Right, so today we're going to start chapter 6, and the next two chapters basically going to take us through trigonometry. So I just want to start by looking at the word itself and see if there's a prefix or a suffix or something in there that we might recognize. Does anybody recognize anything in that word? Part of it that might mean something. Yeah, Caleb?
Try.
Try? Okay, what does that mean?
3.
3. All right, so that usually means we have 3. Anything else there? There's actually a couple other things there that you might recognize. Oh, Leo, you see anything?
It ends in the same way that geometry does.
Okay, it ends in the same way as geometry. It says different subjects or different parts of math that end in the word metry, and that means measurement. But that still leaves one thing, gone. You know what gone means, or where you see that a lot in math? Yeah?
Wouldn't it be like the sides, or like both sides?
Yeah, when we talk about like polygons, we use a lot of terms that end in the word gone, like hexagon, octagon, things like that. So gone is it's like a sided shape. So then we're talking about 3-sided shapes. And in fact, if you put the first two together, trigon, that's another name for a triangle. Basically, every 2D shape in math, there's a way to name it ending in gon. Okay, we don't use the word trigon a lot. We usually use triangle. Same with a 4-sided shape. A lot of times we call it a quadrilateral, but you can also call it a tetragon. Because tetra means 4. All right, so we're really looking at measuring 3-sided shapes. Okay, that's a big part of trig. So just kind of as an example, very simple one, is let's say you had a building and you were standing 50 feet away from the building, and you had a device where you could measure from where you're standing to the top of the building. You could measure the angle, okay, the angle of elevation. That's what we call it, from the ground up towards the top. And that device, a lot of times it's used by surveyors, okay? Like it's called a transit, and they can measure angles and distances with it. So let's say you use that device and you measure an angle of 30 degrees. Well, what we just did is we created a triangle right there. And assuming that the building is straight to the ground, what kind of triangle would that be in red? Yeah, it would be a right triangle. So now using right triangle trigonometry, we could find how long that side of the triangle is, which really means the height of the building. And we don't just work with right triangles. Sometimes we have to work with triangles that don't have a right angle. Okay, so it's a little bit harder because then we can't use things like Pythagorean theorem. You can only use that if you have a right triangle. SOHCAHTOA, if you're familiar with that from geometry, like opposite over hypotenuse and that stuff. If you don't have a right angle, you don't have a hypotenuse. Okay, so you can't use any of that. But when we do have right angles, I think some of the stuff you learn in geometry, we'll start to look at that. So we'll do some things in trig that are very numeric, okay, calculation-based. We're going to do some things where we take trig functions and rewrite them. So for example, if you're familiar with the trig functions, sine, cosine, and tangent are 3 of them. Well, it turns out that if you take the sine and divide by the cosine, you always get the tangent. Okay? Always. It's just that it's a special formula, and it's called a trig identity. So we'll spend a good week, or maybe a little more, talking about trig identities. Okay? And that's going to be very useful in calculus, right? Because in calculus, if you had to do something with this versus doing something with that, it's a lot easier to work with something that's not a fraction, okay, than something that is. So we'll look at ones that are even bigger than this and try to simplify them. So we'll spend a little bit of time on trig identities. So it's kind of a mixture. It's a mixture of some things that are really numerical based and some things that have nothing to do with numbers at all. All right, so let's just start out by talking about really the basics of really basic things in trig, which is what's an angle. And so an angle is made up of two rays that have a common starting point called the vertex. And that's the definition of an angle if you're just going to draw it by itself. Okay. We still call this thing that I just circled, that's an angle. Even though it's not between two rays, it's between two line segments. But when you draw an angle inside of a triangle, that's inside of another shape. This definition is when you draw an angle just all by itself, like this. Two rays, common vertex, common starting point called the vertex, and that's an angle. In that angle, one ray is the initial side and the other ray is the terminal side. And the way you can figure out which side is which is you start at one side, you move inside the two rays, okay, not on the outside of them. So stay in between the rays and go in a counterclockwise direction. So if I'm inside, okay, so somewhere, in that area, if I go in a counterclockwise direction, where I start is the initial, where I end is the terminal. Okay, and I have to be clear about which angle we're measuring, because really when you draw an angle like that, you have two angles. You have the one that's inside the two rays, and then you have the one that's on the outside. Okay. So that's why I say from a counterclockwise direction between the rays, not on the outside of the rays. Okay, so some of the things we'll talk about with angles is how we measure them. Okay, degrees is one unit, but there's another unit, which we'll see if people are familiar with. Then we can classify angles based on their sides. So we'll talk about different names based on how big it is. And then we'll also talk about the Greek letters that we use in trig to represent an angle. Okay, so any questions on that idea? Definition of an angle, or initial side, terminal side? All right. All right, so when we start to measure angles and sides, we need a way to represent what we don't know. So sides, we already have a way to represent that. If you think of like the Pythagorean theorem, A, B, and C are generally used, they don't have to be, but generally used for the three sides of a triangle. But now we need names for the angles. And to make it clear, we'll use Greek letters for the angles. So now if you ask me a question and it has a Greek letter in it, I know you're asking me about an angle. If you're asking me a question and you ask me like, well, what is B? I know you're talking about a side, because that's an English letter. Some books, they do it a little differently. They use capital letters for angles and lowercase letters for sides. I think that gets confusing, especially when you're trying to talk to someone. Because if you ask me, well, what's C? I'd have to say, well, do you mean capital C or lowercase c? Which one are you talking about? And even on paper, if I draw something like that, you can't tell, is that capital or lowercase? There's no context, or there's no sentence around it to figure out the size of it. So Greek letters kind of simplify all that. So these are some of the Greek letters that we'll use. Does anybody know the name of that first one? The first one there, that is the first letter in the Greek alphabet. Does anybody know it now? Yeah? Yeah, that's the Greek letter alpha. And then the second letter there kind of looks like a B. That's, yep,
Beta.
yep, that's beta. And that one that kind of looks like a Y, but it's not quite, that's gamma. And when we're talking about solving triangles, those are the three that we use quite a bit. Alpha, beta, and gamma. Yeah?
Oh, I know the next
Oh, you know the next one? Sure, what's the next one?
Theta.
Theta? Yep. And does anyone know the last one? Might have seen the capital version of it. It looks like this. Does anybody know what it is now?
Omega.
That's omega. All the letters I showed you here are lowercase. The capital version, some of them look just like the English letters. Some of them definitely don't. Okay, and we're not going to use them all today, but now you have at least some variables you can use when you want to label an angle that you don't know. Right, so when we sketch angles, which we're not really sketching with protractors, that's not really the point of trig, to sketch things and make constructions, that's more what you do in geometry. But when we do make a rough sketch, usually we're going to sketch angles in what's called standard position. Without this, if I said to everyone in here, draw a 45-degree angle, some people might draw it like that, or some people might turn it and draw it different ways. So by having you draw it in standard position, it gives a way that everyone's would look the same. So sketching an angle in standard position means the vertex of the angle is at the origin, and the initial side is on the positive x-axis. Okay, so there's an angle that's in standard position. Okay, so two things have to happen. Vertex at the origin, initial side on the positive x-axis. If I put the angle like that, is that in standard position? Caleb?
No.
No, why? What's wrong with it?
The vertex isn't in the origin.
Yeah, the vertex in that case is not at the origin. And if I did something like this, how about now? Is that angle in standard position? Yeah.
No,
No, why not?
because it's on the negative x-axis.
It's so why isn't it in standard position?
Because it's not on the positive x-axis.
Right, the initial side is not on the positive x-axis. Now the initial side is on the positive y-axis. That's not where it needs to be. Okay, so standard position, just like that. Okay, so one way we can measure an angle is in degrees. We haven't gotten to it yet, but does anybody know the other units that we use a lot? I mean, there's several ways, but there's a way in math and trig, especially calculus, that you use a lot. Yeah?
Radians?
You're going to use radians. Okay? And at first, it might seem like degrees is the more common one, and probably up until now it has been. But when you get to calculus, degrees is kind of the weird one. It's like the one that you don't use. You use radians all the time. All right, so we got to kind of get used to converting between the two. But first, let's talk a little bit about degrees. All right, so if you were, let's say, on a circle, and you started here, and you made one complete revolution, and went right back to where you started with, essentially your displacement is zero. You've gone back to where you started. But you have moved a certain amount of degrees. Does anybody know how many degrees if you make one complete rotation? Yeah? It's 360 degrees. Now, if you write it positive Positive implies a certain direction of movement on the circle, which I'll write down in a little bit, but positive is counterclockwise. So if one full revolution is 360, how much would a half counterclockwise revolution be? Yeah,
180.
it would be 180. And if we did a quarter revolution, it would be half of half, which would be 90. Okay, so as I kind of mentioned before, angles that are measured counterclockwise are positive. Angles that are measured the other way, okay, if you go clockwise, are negative. And I'll show you, I have a little program I can draw angles in standard position and just kind of show you what that would look like. Okay, so let's take a look at just sketching some angles in standard position. Let's see what it looks like. Alright, so there's basically a 0 degree angle. It's 0 is always on the positive x-axis to the right. Now what I can do is I can move the terminal side, but I can't move the initial side. And I can't move the vertex. So every angle that I draw here is always in standard position. If you go straight up to the top, that's 90. And you're seeing another number below it. We'll talk about what that is, but you might already have a guess. Okay. Halfway around is 180. Okay, that's 3/4, that's 270. And 360 all the way around. Now, if you go back the other way and bring the rotation clockwise, that's when you can start to get into negative angles. And you'll notice for some angles, it writes them as a decimal. And then for some, it's writing it as a fraction with pi. There's generally a pattern to which ones it's doing that for. If you look, just to make it easier, let's look at positives. All right, nope, it doesn't do that one. But it does 22.5. It does 30. It's going to do 45. It would do 60. Right? So there's just certain angles that we write as multiples of pi, and that's generally the angles that are multiples of 30 and 45. I'm kind of surprised it did that 22.5 one. I see what it's doing there. It's half of 45, but that's not a common one. Angles that are multiples of 30 and 45. And there's some overlap there too, like 90. It's in both. And then if you go around more than once, to indicate that, if you had to on paper, you can just draw it kind of as a spiral. We generally don't do that, but that's how you could do it if you had to. And you could just keep going as many times as you want. So any questions on positive and negative angles? So this is actually kind of good once you get used to working in radians and degrees. You can try some, especially like the negatives and the radian ones, and see if you can get an idea of where you would end up. Like hopefully, eventually you'll know that that area is negative pi. And usually it gives you a little green check mark. There you go. So by the end of chapter 6, you'll pretty much be able to figure out where everything is very, very quickly. Okay. Negatives, positives, radians, or degrees. Okay, so an angle that's larger than 360 just means you've gone around more than once. Generally, though, when we're trying to write like a final answer to a problem, if the answer was an angle, and it had to do with movement on this circle, we want it between 0 and 360. Right? So rather than telling somebody, well, my angle is negative 180, just give it to them as a positive. It's the same spot, positive 180. Right? Same thing, let's see. if I had an angle of 450? Well, a simpler way to say that is just to say 90. If you don't care about how many times you've gone around, you just care where you've stopped. 90 and 450, for the purposes of doing trig, are the same number. And the two angles that I just mentioned, a 90-degree angle and a 450-degree angle, are called coterminal. The reason they're coterminal is they have the same initial and terminal sides. Okay, so if you sketch 90, there's your initial, there's your terminal. If you sketch 450, the initial and terminal are in exactly the same spot. There's your initial, there's your terminal. So what's the connection between 90 and 450? Anybody think of arithmetic-wise what you could do to 450 to turn it into 90? Yep. Okay, let's try another one and see if that always works. Let's take, I'll tell you that positive 180 and negative 180 are exactly the same. Does dividing 180 by 5 convert it into negative 180? No. So it did work for that specific one, but it doesn't work in general. Did anybody see how you could turn negative 180 into positive 180? Or 90 into 150? 450? Same idea.
Add 360.
Yeah, add or subtract 360. So anytime you want to find a coterminal angle, if you just add a revolution, that will give you another angle that's coterminal. And we can do that in degrees, or once we learn radians, we could also do it in radians. Of course, if you're doing it in radians, you wouldn't add or subtract 360. You would have to add whatever 360 is equal to in radians. Okay, so what we're going to do is just practice sketching a few angles in standard position, and then we'll find a negative and a positive coterminal angle, just by adding and subtracting 360. Right, so first angle is 30 degrees. Okay, I'm not looking for the sketch to be perfect. I'm not checking it with a protractor. But if you drew 30 degrees, something like this, that's not really close. Okay. So could anyone describe to me where the terminal side would be for a 30-degree angle? Yeah.
A little less than like halfway lower than the box. Because like a 45 would be directly diagonal through the first quadrant.
Yeah. So a 45 would go right through the, it would be like a line with a slope of 1. So we're going to go a little bit less than half. I don't know if that looks a little less than half. There's a 30-degree angle. Okay, so there's our angle. And now we're going to find an angle that's coterminal with it. Positive and a negative. Okay, so what would be a coterminal angle for 30 degrees? That's positive. Yep, Megan?
390.
390. And how did you get that?
I added 360 to it.
Yeah, just added one revolution. So if you wanted to show that as a 390-degree angle, what you could do on paper is that. Now you're showing you've gone around one full time and then a little bit more. Okay, so 390. And what about a negative angle? Yeah?
Negative 330.
Negative 330. Again, you could indicate that by having the spiral go the other way. That's a negative 330 degree angle. Any questions on that? All right, so there's 30. Let's take a look at 145. Now, how come I can always put the initial side right there? What in the directions is basically telling me to always do that? Yeah.
It says in the standard position.
Right. It says to sketch it in standard position, and part of that is the initial side is always on the positive x-axis, and vertex is at the origin. Okay, so how about 145? What would that one be? Well, let's start with the quadrant. Gracie, what quadrant would that be in? Which one?
Upper left.
Upper left, yes, quadrant 2. Now, after a while, we're just going to get much better at knowing these numbers, but 135 is the average of 90 and 180. Okay? 135 is exactly between the two. So 145 is a little more than halfway. So there's our angle. Okay, now we'll find two angles that are coterminal. Positive, negative. So Dylan, what would be a coterminal angle for 145 that's positive?
505.
I think, so if you take 360, oh wait a minute, no, you're right, I'm wrong. Yes, I had to think for a second. 505, 360 plus 145, yep. Okay, and how about a coterminal angle that's negative? Yeah?
Negative 215.
Negative 215. You can always double check it just by taking 215, 145, add them up, and they should add up to 360, which they do. Okay, so there's 145. Any questions on that? Okay, let's try one that starts off as a negative angle. Okay, so Abby, what quadrant is my terminal side going to be in this time?
Fourth quadrant.
It's going to be in the fourth quadrant, and can you kind of describe where in the quadrant?
It'll be like a line with the slope of -1, so it'll be like straight from the middle.
Yeah, exactly. It's going to be on a line with a slope of -1, going right, splitting the quadrant right in half. So there's negative 45 degrees. And two coterminal angles. Well, the positive, I'll do that one, would be 315. If you add 360, how about the negative? Sam?
Negative 375. No. Negative 405.
Yeah, negative 405. Okay, so the point here is there's lots of ways, if you had a picture, to write down what you're seeing if it's not labeled as an angle. But the way we generally want to do it is to pick angles between 0 and 360, and that's how you do it. You find an angle that's coterminal and add or subtract. Sometimes you would have to do it more than once. Like if I said to you, I have a negative 900 degree angle. What's that equivalent to as a positive? Just keep adding 360 till you get it, the first positive answer you get. All right, so we're going to look at some definitions having to do with the size of an angle. And the Greek letter that I'm going to use to represent my angle is theta. Okay, what's the definition of an acute angle? Remember that? Acute angle. Megan?
An angle that has a measurement of less than 90 degrees.
Okay, it's less than 90. And there's one thing we have to add to that. I agree, it definitely has to be less than 90, but I can think of an angle that's less than 90 that would not be acute.
Does that have to be like greater than 0?
And it has to be greater than 0. Okay, so an acute angle, you wouldn't say -10 is an acute angle. Because it's negative. In fact, you wouldn't even say 0 is an acute angle, because if your angle is 0, do you even have an angle? Not really. Because the initial side and the terminal side are the same. So acute angle, greater than 0, less than 90. How about right angle? What's the measure of a right angle, Leo?
Exactly 90 degrees.
Exactly 90. Okay, and then an obtuse angle. What's the definition of obtuse, Gracie?
Greater than 90.
Greater than 90, and one other thing. It's between two numbers. Juliana?
Would it be less than 36?
Yeah, we have to be a little more restrictive than that. It has to be less than something, but it can't go that big. Yep.
180.
Yeah, it has to be less than 180. Sometimes when an angle gets bigger than 180, we call that a reflex angle. Okay, not a term that we really use or talk about a lot, but strictly for an obtuse angle, it should be between 90 and 180. Okay, so all of these definitions just apply to a single angle. The next definition applies to multiple angles. Okay, you need two of them to do this one. How about complementary? Anybody remember what complementary angles are? Leo?
It's two angles that add up to 90 degrees.
Two angles that add up to 90. Yep. And one more thing about the angles. What do you think the angles? Because for example, I can think of two angles that add up to 90 that are not acute. Or no, I'm sorry, that are not complementary. Anybody know the other condition you have to have? Yeah?
They have to be acute.
Right, I kind of said it on accident. They have to be acute. Or in other words, they have to be positive. For example, if you had -10 and 100, those are not complementary. They do add up to 90, but they have to be acute angles that add up to 90. How about supplementary angles? What's the definition here? Yeah?
Two positive angles that add up to 180.
Yeah, two positive angles that add up to 180. So for supplementary, could I say two acute angles that add up to 180? No? How come?
Because they're less than 90, and no two numbers add up to 180 that are less than 90.
Yeah, so they couldn't be acute. So to have supplementary angles, you have to have at least one obtuse. In fact, you have to have exactly one obtuse. Or, I guess they could both be right. So there's really two cases for supplementary. They're either both right angles, or one obtuse, one acute. Caleb, is that what you were going to say? Yeah. But they definitely can't both be acute. So the point here of saying positive is that negative angles don't have complements or supplements. Okay, so now we'll just look at some examples and practice finding what the complement is, which means what do you add to get 90 to it, and what the supplement is. Okay, let's start with 48 degrees. Okay, what would be the complement of 48 degrees? Tessa?
Is
a complement of 48 degrees. Yeah, 42. So because if you add 48 and 42, you get 90. How about the supplement? What would be the supplement of 48 degrees, Sean?
132.
132, yeah. In fact, once you have the complement, you could just do something with that to get the supplement. Can anybody think what, if you wanted to write a formula? Well, actually, let's write it like this. The formula for the supplement is, Gracie?
C plus 90.
Yeah, it's the complement plus 90. And then you could rearrange that different ways to figure out. Like you could get C by itself. And basically it would say C equals the supplement minus, oh, I'll just show you. That's another way you could think of it. If you take the supplement and subtract the complement, you would always get 90. Or the opposite of the complement is 90 minus the supplement, which is the same as saying the complement is the supplement minus 90. So all different ways you can kind of think about it. Hey, negative 18 degrees. What's the complement of that?
The reason there's complement, negative degrees can't have complement.
Yeah, there is no complement. So those formulas I wrote on the right-hand side, that's assuming you have a positive angle. So that doesn't apply. Same thing with the supplement. Doesn't apply. Okay, last one. It's kind of like the formulas. We're just going to come up with a formula. We already came up with it, really. But let's just do it for x. Okay, what's the formula for the complement? Assuming your angle is x degrees, and assume x is positive. X is not a negative number. Yep.
90 minus x.
Yeah, 90. 90 minus x. And that's degrees. Okay, the formula for the supplement, well, we didn't quite write it this way, but what would the formula for the supplement be? Just using your angle. Okay, forget about the complement. Just, yep.
180 minus x.
Yeah, it would be 180 minus x. Again, assuming x is a positive number. Okay, any questions on that? All right. So earlier I said to you that there's another way to measure angles, and that other way is radians. Okay, so the first thing I'm going to do is I'm just going to start off by showing you something that's more geometric, okay, less numeric based, okay, something that's more of a picture of a radian. And I'm going to use this picture. So what I've done is I have a circle, and inside the circle I put an angle. The vertex of that angle, which is point C, is right at the center of the circle. Both of the rays come out from point C. So we have ray CA, that's the terminal side, ray CB, that's the initial. As the rays come out from the center, they hit the edge of the circle here and there. If I connect between points A and B, following not as a straight line, but following the curve of the circle, that is an arc. Okay, that's arc AB. And it's called an intercepted arc because it's where the rays intercept or intersect the circumference of the circle. Okay, any questions on that? All right, so angle ACB, okay, would come out to exactly 1 radian if something special happened. Okay, and what the special thing that would have to happen is if you took a piece of string and measured arc AB. Okay, so lay a piece of string on that arc, measure it exactly, then straighten it out, get the distance of it. Then measure the radius. If the size of the arc and the size of the radius came out exactly the same, then you've just drawn an angle that is 1 radian. So again, the size of the arc would have to come out to be exactly the same as the size of the radius. And even if you just look at the 2 words, RADI, RADI, they both start with those 4 letters. So that's why there's a connection between the 2, radian and radius. Now, that doesn't always have to be true. Just because you sketch an angle, it doesn't mean that the size of the arc and the radius are the same. Look at that angle. Now you have an arc right there, and your radius is right there. The radius is much, much longer, and the arc is much shorter. So since the arc is shorter than the radius, the angle is going to be less than a radian. Okay. We could also look at it kind of the other way. Now you have an arc right here that is much bigger than the radius. If the arc is bigger than the radius, the angle is bigger than 1 radian. Okay? It's only 1 radian if they come out exactly the same. So any question on that idea? It doesn't really tell you anything numerical about a radian. It just shows you the connection between a radian and a radius. That's what it does. Now we're going to look at something more numerical. Does anybody already know the conversion between radians and degrees? Right, let's say I wanted to convert feet to inches. Can somebody tell me the connection between feet and inches? Yeah.
There are 12 inches in a foot.
There are 12 inches in 1 foot. How do you know that?
Because those 2 things are equivalent.
How do you know they're equivalent?
Because that's what we're taught.
That's what you're taught. All right, someone told you that, right? So the point is, you have to start with something that you can't really prove. It's just kind of a definition. Well, that's basically what we're going to come up with here. We're going to come up with a definition. I'm going to tell you something that you just have to trust me it's true, and that's going to help us to figure out the conversion between degrees and radians. And the definition that I'm about to tell you, it's going to have something to do with what's called a unit circle. Okay, a unit circle is a circle that has a radius of 1. That's all. Just a circle with radius 1. Now, in a unit circle, there's something special that happens. There's a connection between, if you draw an angle in that circle, there's a connection between the size of this arc and the size of this angle. In a unit circle, a very special connection. Okay, and the connection is that in a unit circle, if you draw an angle and you measure the angle in radians, okay, and write that number down, and then you measure the length of the arc and write that number down, those 2 numbers will always be the same. Okay, so you could try it. If you had a protractor, maybe a compass, you could try sketching it and drawing it. Okay, but those two things would always be the same in a unit circle. So if you measure the angle in radians, not degrees, if you measure the angle in radians, and you measure the length of the arc, those two numbers would always come out exactly the same. And of course, for the measurement of the arc, like with a piece of string, you have to use the units that you used for your unit circle. If your unit circle was a 1 foot circle, you measure your arc in feet. If your unit circle was a 1 inch circle, you measure your arc in inches. You have to stick with the same units, obviously. Okay. So what that means is if we want to figure out how many radians to go all the way around, what else could I figure out that would be equivalent to that based on this definition? I want to figure out how many radians to go all the way around the circle, but I can do that a different way because that number of how many radians to go all the way around the circle is equal to something else in the circle. Yeah? It would be equivalent to the arc that goes all the way around the circle. Okay? A number of radians to go all the way around the circle, that's your angle. The arc that goes all the way around the circle is going to be equal to it. So what's the name of the arc that goes all the way around the circle?
The circumference.
Circumference. Okay, the circumference is just an arc, it's just a special arc that's the whole circle. So if I can find the circumference of that circle, the circumference is going to be the same as the angle in radians. And that's how we're going to figure out how many radians to go all the way around the circle. So let's find the circumference. What's the formula for circumference of a circle? Remember that from geometry? Anyone have well, what is it? It has something in it. Every formula with spheres and circles always has this in it.
Pi.
It's got pi in it. Anybody remember what else? Circumference, yeah?
It includes the radius.
Yeah, you end up multiplying by the radius, doubled. So you could think of it as pi times diameter or 2 pi r. Same thing. So, in a unit circle, what is the radius? 1. So that means the circumference of this circle is 2 pi units, which is exactly equal to the measure of the angle in radians to go all the way around the circle. So the conversion is there are 2 pi radians in 1 revolution of a circle. So we just did the so part, everything after that. If we can find an angle that we know the arc length and all that, that's what we just did. So now we know that in 1 revolution, it's 2 pi radians, which is the same as 360 degrees. So here's your conversion right here. 2 pi radians equals 360, just like 1 foot equals 12 inches. Okay? It's just a fact that is true. Just like 1 foot equals 12 inches. Somebody told it to you, well, I'm telling that to you. 2 pi radians equals 360 degrees. But it's more than I just told it to you. I tried to explain why it's true based on another fact, which we haven't proven, but can't prove everything. Right, so 2 pi radians equals 360 degrees. How could I write that a little simpler? I could kind of reduce each side by dividing by what? Yep. You could divide each side by 2 and say pi radians equals 180 degrees. But usually when you give someone a conversion, it has a certain number in it. That number is not part of that conversion. It is part of the one Caleb gave me, but it's not in this one. What number do you usually have when you tell someone a conversion between two things? A 1. Okay? He said to me, in 1 foot there's 12 inches. He could have said in 4 feet there's 48 inches. That conversion would have worked as well. But usually we give it to somebody with a 1. So let's get a 1. Let's get a 1 on the right. Getting a 1 on the right is going to enable us to convert one way between degrees and radians, and then we'll do it again on the left, and that will be the other way. So what would I have to do to each side of that to get a 1 on the right? Yeah?
Divided by 180.
Yeah. So I'd have pi over 180 radians equals 1 degree. So now if you said, okay, well, that's 1 degree converted to radians. What about 3 degrees? That's easy. Multiply each side by 3. If you said, well, what about 12 degrees? 1 times 12, pi over 180 times 12. You basically take whatever you want to convert, and that's the key right there. You multiply by pi and divide by 180. That's the 2 steps to convert from degrees to radians. Multiply what you want to convert by pi, divide it by 180. Okay, we'll figure out the other way in a second. Multiply by pi, divide by 180. Okay, let's look at the same thing again. This time, let's get a 1 on the left. Okay, what would I have to divide each side by here to get a 1 on the left? Yep. Divide each side by pi. So then I would get 1 radian equals 180 divided by pi degrees. So if you want to know how many degrees are actually in a radian, do 180 divided by 3.14, and that's an estimate you can use. Right. Now, using the same idea, what if I wanted to know 5 radians equals how many degrees? What could I do to both sides of that equation? Yeah. Yeah, take whatever you want to convert, which in this case is a 5, multiply by 180, because the 180 is in the top, and divide by pi. If you wanted to convert 7 radians, take 7 times 180 divided by pi. So in that case, you multiply by 180 and divide by pi. And to convert between the two, it's very similar, so it's easy to mix up. Is it 180 over pi, or is it the pi and the divide by 180? Which way is it? Well, if you can just remember that when you think degrees, that's the number I want you to think of. Okay, so I'm going to ask you that in a second. When you think degrees, think 180. When you think radians, think pi. Okay? So pi, think radians. 180, think degrees. And if you remember that's all you need to remember. You don't even really need to remember this. So let's convert 30 degrees to radians. So here, the problem says you're converting 2 radians. So that means degrees has to disappear. Well, if you think of it as a fraction, right now degrees is in the top. I'm going to multiply by another fraction, and I want degrees to cancel out. So where would degrees have to go in the fraction on the right to cancel it out in the one on the left? Yeah? It would have to go in the bottom. That means radians has to go in the top. That's just dimensional analysis, right? The units have to cancel out. Now, if you just remember what I said, what's the number I said to always think of when you think radians? Pi. And the number to think of when you think degrees? 180. There you go. So now, degrees cancels. And generally, we reduce it before we multiply straight across. 30 goes into itself once. How many times does 30 go into 180? 6. And we're left with 1 times pi, which is just pi, divided by 1 times 6. Pi over 6. Generally, when you're converting angles that are multiples of 30 and 45, you leave it as pi. Okay? If they want you to actually round that off to a decimal, they'll tell you. Otherwise, don't. Just leave it. Okay. So any questions on that? You might notice, too, I didn't put RAD, and you don't. Okay? And even right here. We have to get used to not seeing RAD. Okay? When you talk about angles in any level of math, trig and up, the only time you label it is if you want it in degrees. Okay? You put the little circle. If you're talking about an angle and there's no label, it's always radians. Okay, always. Okay, so 45 degrees. So Sam, what would I multiply by here to convert degrees to radians?
Pi.
Multiply by pi, divide by 180. And the reason why, well, you can look at the formula, which has the steps in it, or just think about the units, canceling out degrees. How many times does 45 go into 180? Crazy? 4 times. So 45 degrees is the same as pi over 4. And we could show that very easily. Right there. 45 degrees is pi over 4. All right. 60. Well, let's just do it quick. Anyone think they could tell me what that would be once you reduce?
Pi over 3.
Yep, pi over 3. And let's try one with a negative. Let's do negative 90. Negative doesn't change anything, other than when you write your final answer, put a negative in front. Okay. Anyone think they could tell me what negative 90 would be in radians? Yep.
Negative pi over 2.
Negative pi over 2. Perfect. Okay, any questions on that? Yes?
If we're finding a coterminal angle and they give us a radian, do we just convert it to degrees first, or will we not really be asked to do that?
So if they gave you an angle and said to find an angle that's coterminal with that, what do we do in degrees? You add or subtract how much?
360.
You would add or subtract 360. Well, 360 is the same as 2 pi. So you would add or subtract 2 pi. You would keep the problem in radians and just do it that way. I think it's going to be more work to change that to degrees, add 360, and then change it back. So if you had to add 2 pi, the way you have to do it is you need a common denominator. So negative pi over 2 plus 4 pi over 2. So an angle in radians that's coterminal to negative pi over 2 is 3 pi over 2. That's negative 90. That's 270. Okay, so that is a little more work to find coterminal angles in radians just because of the arithmetic with fractions. And of course, if you did minus, then you could find another coterminal that's negative. All right, let's try converting to degrees. Now, for this one, I'll pretend like radians is written, but we got to get used to not seeing it. Okay, but I'll do it on this one. Okay, so convert to degrees, that means radians has to drop off. Okay, where would the radians have to be to cancel out? On the bottom. That means degrees is in the top. Number we always think of when you think degrees, that's the 180. And radians, pi. Okay, what's going to cancel out when you multiply straight across? Yeah?
The 2 and the 180.
Okay, we can reduce that. And now what cancels out completely? The pi's. And what else? radians, yeah. So all you're left with is 3 times 90. And 3 times 90 is how much? 270? Do I need to put any label on it? Yes, because it's in degrees. What if I just wrote that as my answer? What's that? It's 270 radians. Very, very different than 270 degrees. It's like saying 12 feet versus 12 inches. It's totally different. Okay, any questions on it? Let's try this one. Eventually, the reason I did that part quickly for you is because you realize when you're converting radians to degrees, all you have to do is change pi to 180. So it's really 2 times 180 divided by 3. The pi's always cancel out, if there's a pi to start with. If there isn't, then you're probably going to write your answer as a decimal. Okay, so how much is 2 pi over 3? Yep.
120.
120. The way I do that one in my head is I haven't memorized what 30, 45, 60 are. So I know pi over 3 is 60. I just haven't memorized. So it's pi over 3 doubled. So if pi over 3 is 60, double it, I get 120. Same thing, if you ask me to convert this one, I would just say in my head, well, that's 60 times 4, 240. So eventually you learn a few tricks to kind of speed things up. And I'll show you how I would use the trick here. That's 45. So really, this is just 45 times 5, if I was doing it in my head. If you weren't sure how to do that trick at first, you just multiply by 180, divide by pi, pi's cancels, and then 4 goes into 180, 45 times, and now you're 5 times 45, which is what I just said. And that's just another one. Okay. All right, so let's try one where we actually round it. So for this, there's no point in reducing. You're just going to type it all into the calculator. Okay, 500 degrees. Trevor, can you remind me, what do I multiply by to change degrees into radians?
Pi over 180.
Yep, pi over 180. And now, do you think when I type in pi, should I use the pi button or 3.14?
Pi.
Yeah. Using the pi button is always going to be more accurate. 500 times pi divided by 180. You can type it like that because it's order of operations is fine. 8.23. And what's my unit on that? Yep. So should I write that? No. 8.23 radians. Let's try converting a radian to degree and then rounding it off. Okay, so you multiply by 180, divide by pi. And on this one, I'll show you what happens if you use the pi button versus 3.14. It'll make a pretty good difference. 3 times 180 is 540, divided by pi. So that's 171.89. Now let's take 540 and divide by 3.14. So instead of 171.89, we get 171.97. That's quite a bit different. It's not like you got 171.88 and 171.89. It's not like they were that close. 89 versus 97. That's definitely off a little bit. Okay. So always use the pi button. And where that would be really important is pretend you were navigating from Boston to Europe. Well, if you travel at, a heading, I'm not saying that would be the heading, but if you travel at a heading of 171.88 versus 171.97, by the time you get where you're going, you might be hundreds of miles off track because you traveled so far at an angle that was a little bit off. So, makes a difference. Right, so the homework is on 323. And it's a lot of fast problems. Find the complement, find the supplement, that kind of stuff. So it's 1 through 4, 7, 9, 11, 12, 15, 24 to 26, 30 to 32, and then 35 to 37, 41 to 43, 47, and 51 to 53. Okay, so we'll take a look at the homework tomorrow. And then we'll finish up section 6.1 tomorrow, and we'll start section 6.2.